There is a boundary in space where reality itself stops making sense. A point where time freezes, where light gets trapped forever, and where the laws of physics as we understand them simply break down. This boundary is called the Schwarzschild radius, and it defines the edge of something so terrifying that even Einstein refused to believe it could exist. When most people imagine a black hole, they picture something impossibly small. A point of infinite density, perhaps. A pinprick in the fabric of space. The reality is far more unsettling. Black holes have size. They have dimensions you can measure, boundaries you can calculate, and some of them are incomprehensibly large. Tonight, we're going to journey from black holes the size of small cities to monsters so massive their event horizons dwarf our entire solar system. We're going to visit Sagittarius A star, the sleeping giant at the heart of our galaxy. And by the end, you're going to understand why the true scale of these cosmic abysses is not just mind-bending, it's genuinely terrifying. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. The year was 1915. The world was at war. Trenches scarred the European landscape like wounds that would never fully heal. Artillery shells screamed overhead, turning farmland into craters and villages into rubble. Young men died by the thousands in the mud of battlefields, whose names would become synonymous with horror. Verdun, the Somme, Ypres. These places consumed an entire generation. And in the midst of all this chaos, on the Russian front, where German forces pushed eastward through frozen forests and desperate villages, a German artillery officer named Karl Schwarzschild was doing something remarkable. While calculating trajectories for howitzers by day, he was solving equations by night. Not just any equations. The most complicated equations in physics. The equations that describe the very fabric of reality itself. Schwarzschild was not a typical soldier. Before the war, he had been one of the most brilliant astrophysicists in Germany, perhaps in the world. He had studied the structure of stars, the behavior of light passing through Earth's atmosphere, and the mathematics of celestial mechanics. He had been the director of the Astrophysical Observatory in Potsdam, a prestigious position that placed him at the forefront of astronomical research. When war broke out in 1914, Schwarzschild volunteered for military service despite being over 40 years old. He felt it was his duty to his country, but even in the trenches with the sounds of war echoing around him, his mind couldn't stop working on physics. Just months before Schwarzschild arrived at the front, Albert Einstein had published his general theory of relativity. This revolutionary theory described gravity not as a force pulling objects together, not as some invisible string connecting massive bodies, but as a curvature of space and time caused by mass and energy. Einstein had completely reimagined how the universe works. Think about what this means. Before Einstein, we thought of space as a fixed stage upon which events played out. Space was just emptiness, a void that objects moved through. Time was separate, ticking away at the same rate everywhere in the universe, a cosmic clock that all observers could agree on. Einstein showed that this picture was wrong. Space and time aren't separate. They're woven together into a single fabric called spacetime. And this fabric isn't rigid. It's flexible. It can stretch and bend and curve. Massive objects like stars and planets don't just sit in spacetime. They warp it. They create dips and curves in the fabric, and other objects follow these curves as they move. That's why planets orbit the sun. They're not being pulled by some mysterious force acting across empty space. They're following the curved geometry of spacetime around the sun. The sun's mass creates a depression in the fabric of reality, and the planets roll around the edges of this depression like marbles circling a drain. Einstein's equations described exactly how mass curves space-time. They were beautiful in their symmetry and profound in their implications, but they were also incredibly complicated. The mathematics involved was so difficult that Einstein himself had only found approximate solutions. He could describe general principles, but actually solving the equations for specific situations seemed nearly impossible. Einstein wasn't even sure exact solutions could be found. Schwarzschild, sitting in a bunker on the Russian front with artillery fire in the distance, and the cold of a Russian winter seeping through the walls, found the first exact solution. He solved Einstein's equations for a simplified case, a perfectly spherical, non-rotating mass sitting alone in otherwise empty space. This isn't quite realistic. Real stars rotate, real stars have companions, real space isn't empty. But the simplified case captured the essential physics, and Schwarzschild's solution described exactly how space-time curved around such an object. He sent his calculations to Einstein in Berlin. Einstein was astonished. Here was a complete, exact solution to his equations, derived by a soldier on the front lines of a war that was consuming Europe. Einstein presented Schwarzschild's solution to the Prussian Academy of Sciences in January of 1916. But Schwarzschild's solution contained something strange, something that seemed almost impossible, something that would take decades for physicists to fully understand and accept. There was a special radius at which something bizarre happened. At this radius, the curvature of space-time became so extreme that nothing, absolutely nothing, could escape. Not rockets, not radio, signals, not light itself. Anything that crossed this boundary would be trapped forever, unable to send any signal back to the outside universe. It would be cut off from reality as completely as if it had ceased to exist. Schwarzschild calculated this critical radius with a simple formula. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. Written mathematically, it's elegant. Written in words, it tells you something profound. For any given mass, no matter how large or small, there exists a critical size. Compress that mass within that critical size, and it becomes inescapable. For our sun, the Schwarzschild radius is about 2.95 kilometers. That's roughly 3 kilometers, less than 2 miles. About the length of 30 football fields lined up end to end. Think about that for a moment. Really think about it. The sun is enormous. It has a diameter of about 1,400,000 kilometers. It's so big that you could fit 1.3 million Earths inside it. If the sun were hollow, you could pour Earth after Earth into it for over 1 million times, and still have room left over. The sun contains 99.8% of all the mass in the solar system. Everything else, all the planets, all the moons, all the asteroids and comets, all of it combined is less than a rounding error compared to the sun. But if you could somehow compress all that mass, all 1.99 times 10 to the 30th kilograms of it, into a sphere just 6 kilometers across, roughly the size of a small city, nothing could ever escape from it. Not the fastest rocket ever built. Not a beam of light traveling at 300,000 kilometers per second. Nothing. This boundary, this point of no return, is what we now call the event horizon. And an object compressed within its own Schwarzschild radius is what we call a black hole. The name is perfect. It's black because no light can escape from it. It's a hole because anything that falls in can never come out. It's a region of space-time that's been effectively removed from our universe. Schwarzschild himself didn't think such objects could actually exist in nature. Neither did Einstein. They assumed some physical process would always prevent matter from collapsing to such extreme densities. The Schwarzschild radius seemed like a mathematical curiosity, an artifact of the equations rather than a description of something real. It was like solving an equation and getting infinity as an answer. Mathematically valid, but surely not physically meaningful. Schwarzschild never got to see how important his discovery would become. Just months after sending his solution to Einstein, he contracted pemphigus, a rare autoimmune disease that causes painful blistering of the skin. The disease was essentially untreatable in 1916. Schwarzschild died in May of that year, at the age of 42. The war that he had volunteered to fight in continued for 2 more years, killing millions more young men in the mud of France and Belgium and Russia. The strange boundary Schwarzschild had discovered lay dormant in physics textbooks for decades, waiting to be taken seriously. Waiting for someone to realize it wasn't just mathematics, it was prophecy. Let me explain why this boundary is so significant. Why crossing the Schwarzschild radius means crossing the point of no return. It all comes down to a concept called escape velocity. Every object with mass has an escape velocity. This is the speed you need to travel to escape from that object's gravitational pull and fly away forever, never to return. If you throw a ball straight up into the air, it rises for a while, slows down, stops, and then falls back down. Gravity pulls it back. But if you could throw that ball fast enough, it would never come back. It would escape Earth's gravity entirely and fly off into space. On Earth, the escape velocity is about 11.2 kilometers per second. That's roughly 25,000 miles per hour. About 33 times the speed of sound. Any spacecraft that wants to leave Earth and travel to another planet needs to reach at least this speed. That's why rockets are so powerful. That's why getting to space is so hard. We're fighting against Earth's gravitational pull, and we need to reach an incredible speed to win. The Moon has a lower escape velocity than Earth, about 2.4 kilometers per second, because it's smaller and less massive. It's easier to leave the Moon than to leave Earth. That's why the Apollo astronauts could use relatively small rockets to blast off from the lunar surface. The Sun has a much higher escape velocity, about 618 kilometers per second at its surface. Because it's so enormous, leaving the Sun, if you were somehow on its surface, would require tremendous speed. Now, here's the crucial insight that leads to black holes. What happens if you compress an object so much that its escape velocity equals the speed of light? Light travels at about 299,792 kilometers per second. We usually round this to 300,000 kilometers per second. This speed, represented by the letter C in physics equations, isn't just fast. It's the ultimate speed limit of the universe. Nothing can travel faster than light. This isn't just an engineering limitation that we might overcome with better technology. It's a fundamental law of physics built into the structure of space-time itself. Einstein showed that as objects approach the speed of light, strange things happen. Time slows down for them. Their mass effectively increases. The amount of energy required to accelerate them further increases without limit. To actually reach the speed of light would require infinite energy. To exceed it is simply impossible. So if an object's escape velocity equals or exceeds the speed of light, nothing can escape from it. Light itself gets trapped. Radio waves get trapped. X-rays get trapped. Gravitational waves get trapped. Information itself gets trapped. The object becomes completely cut off from the rest of the universe. The Schwarzschild radius is precisely the radius at which this happens. It's the boundary where escape velocity equals light speed. Cross it, and you're gone forever. Not just for a long time, forever. There is no technology, no clever trick, no amount of power that can get you back out. The laws of physics themselves forbid it. Here's what this means for familiar objects. Because the Schwarzschild radius applies to everything, not just stars. For our sun, as I mentioned, the Schwarzschild radius is about 3 kilometers. The sun's actual radius is about 696,000 kilometers. So the sun would need to be compressed to about 1/400,000th of its current size to become a black hole. That's like compressing a basketball to the width of a human hair. The compression required is almost beyond imagination. For Earth, the Schwarzschild radius is even more extreme. Earth's Schwarzschild radius is about 9 millimeters, less than half an inch, about the size of a small marble. Picture that. You would need to compress the entire Earth, all 6 trillion kilograms of it, every mountain and ocean and continent, every city and forest and desert, all the iron in the core and all the rock in the mantle, and all the water in the oceans, all of it compressed into a marble smaller than your thumbnail. For a human being weighing about 70 kilograms, the Schwarzschild radius would be about 10 to the negative 25th meters. That's a decimal point followed by 24 zeros and then a 1. It's roughly 100 million times smaller than a proton. At scales this small, quantum mechanical effects become important, and we don't really know what would happen. Our theories break down at these scales. But the point is clear. Compressing anything to its Schwarzschild radius requires unimaginable forces. You can't squeeze matter this tightly through any normal process. This is why Schwarzschild and Einstein assumed black holes couldn't form naturally. What possible mechanism could compress matter to such extreme densities? The answer, it turned out, was gravity itself. The same force that holds you to the ground, the same force that keeps the moon in orbit, the same gentle pull that makes apples fall from trees. Given enough mass, gravity becomes unstoppable. In 1930, a young Indian physicist named Subrahmanyan Chandrasekhar was traveling by ship from India to England to begin his graduate studies at Cambridge. The voyage took several weeks, and Chandrasekhar spent much of that time doing calculations. He was thinking about the fate of stars. Specifically, what happens when a star runs out of fuel? What happens when the nuclear fires that hold it up against gravity finally go out? Stars exist in a delicate balance. The nuclear fusion in their cores generates enormous outward pressure, like a continuous explosion trying to blow the star apart. Gravity, meanwhile, is trying to pull everything inward, trying to crush the star down to nothing. As long as fusion continues, these two forces balance, and the star remains stable. But fusion can't last forever. Eventually, the star runs out of fuel. What then? Chandrasekhar discovered something troubling. For stars below a certain mass, about 1.4 times the mass of the Sun, the star could end its life as a stable white dwarf. When fusion stops, The star contracts under its own gravity until it becomes incredibly dense. At this density, the electrons in the star are packed so tightly that quantum mechanical effects kick in. The electrons resist being squeezed any further. This electron degeneracy pressure can hold the star up against gravity forever. The star becomes a white dwarf, slowly cooling over billions of years but never collapsing further. But for more massive stars, even this electron pressure wasn't enough. The gravity of a star more massive than the Chandrasekhar limit, as it came to be called, would overwhelm electron degeneracy pressure. The star would keep collapsing. There was no stable endpoint. This discovery was deeply controversial. Many physicists, including the famous Arthur Eddington, refused to accept it. Eddington publicly ridiculed Chandrasekhar's calculations. The idea that stars could collapse indefinitely seemed absurd, almost obscene. Nature surely had some mechanism to prevent such a catastrophe. Stars couldn't just collapse into nothing. That violated common sense. But Chandrasekhar was right. His mathematics was impeccable. And further research revealed that even for stars that could be supported by electron pressure as white dwarfs, there was another possibility. If a white dwarf in a binary system gained mass from a companion star, it could exceed the Chandrasekhar limit. When this happens, the white dwarf collapses further. The electrons and protons are forced together, combining to form neutrons. The result is a neutron star, an object supported by neutron degeneracy pressure. Neutron stars are incredible objects. They pack the mass of the Sun into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. They spin incredibly fast, some rotating hundreds of times per second. They have magnetic fields trillions of times stronger than Earth's. But even neutron stars have a mass limit. The maximum mass for a neutron star is somewhere between 2 and 3 times the mass of the Sun. This is called the Tolman-Oppenheimer-Volkoff limit. Beyond this mass, not even neutron degeneracy pressure can resist gravity. Stars more massive than this limit have nowhere to go. When they run out of fuel, they collapse. And they keep collapsing. Nothing can stop them. They shrink past the size of cities. They shrink past the size of mountains. They shrink past the size of buildings. They shrink past the size of people. They shrink past the size of marbles. They shrink past the size of atoms. They shrink past the size of atomic nuclei. And eventually, they shrink past their own Schwarzschild radius. When this happens, an event horizon forms. The collapsing matter is now hidden from the rest of the universe behind an impenetrable barrier. It can never send any signal out. It cannot be seen, touched, or detected directly. It is, for all practical purposes, gone from our universe. What remains is a black hole, a region of space-time so curved that everything, including light, falls inward. A boundary from which nothing returns. A Schwarzschild radius made real in the universe. The first strong evidence for real black holes came in the 1970s with the discovery of Cygnus X1. This powerful X-ray source in the constellation Cygnus appeared to be a massive invisible object with a visible companion star. Gas from the blue supergiant companion was falling toward the invisible object, heating up to millions of degrees and emitting intense X-rays as it spiraled inward. The invisible object was too massive to be a neutron star. It had to be something more exotic. It had to be something that couldn't emit light. It had to be a black hole. Since then, we've found many more black holes. We've observed them through their gravitational effects on nearby stars, watching those stars orbit invisible companions. We've detected the gravitational waves released when black holes spiral together and merge, ripples in space-time itself propagating across the universe. And in 2019, we photographed one, capturing the shadow of the supermassive black hole in the galaxy M87 against the glowing gas swirling around it. Schwarzschild's mathematical curiosity had become reality. The boundary he calculated in a trench during World War I, while artillery shells fell around him and his country consumed itself in war, describes real objects scattered throughout the universe. Objects so strange that they once seemed impossible. Objects so powerful they trap light itself. Objects whose very existence challenges our understanding of physics. The Schwarzschild radius is not just an equation, it's the edge of oblivion. But there's something even stranger about this boundary, something that goes beyond just trapping light and matter. The event horizon is a place where time itself behaves in ways that defy intuition. From the perspective of someone far away from a black hole, watching an object fall toward the event horizon, something bizarre happens. The falling object appears to slow down as it approaches the Schwarzschild radius. As it gets closer and closer, it seems to move more and more slowly, as if swimming through increasingly thick molasses. Light from the object becomes increasingly redshifted, stretched to longer and longer wavelengths as it struggles to climb out of the intense gravitational field. The object grows dimmer and redder. Its movements become sluggish, then glacial. At the exact moment the object reaches the event horizon, from the outside observer's perspective, time appears to stop. The object seems to freeze at the boundary, locked forever at the edge of the black hole. It never quite crosses. It just fades away, frozen in time, growing dimmer and redder until it redshifts into invisibility. But from the perspective of the falling object itself, nothing special happens at the event horizon. If you were falling into a sufficiently large black hole, you might not even notice the moment you cross the Schwarzschild radius. There's no sign, no barrier, no wall, no flash of light. You would simply find that no matter how hard you tried, you could never send a signal back out. You've crossed a one-way door in space-time. This disagreement between perspectives is one of the most mind-bending aspects of black holes. Both perspectives are correct. Both are valid descriptions of reality. Time simply runs at different rates depending on where you are in a gravitational field. What happens inside the event horizon? Once you've crossed the Schwarzschild radius, all possible futures lead to the singularity. You cannot avoid it. It's not a place in space that you might be able to steer around. Inside the event horizon, the singularity is your future. And you cannot avoid your future any more than you can avoid tomorrow. This is what Schwarzschild discovered while solving equations in a bunker during the worst war humanity had ever known. A boundary where space and time trade their roles, a point of no return that exists for any mass compressed within its critical radius. For our sun, that radius is about 3 kilometers. For the collapse cores of massive dead stars, that radius corresponds to black holes roughly the size of small cities. And as we're about to see, these city-sized monsters are just the beginning. The universe contains black holes at every scale the laws of physics allow. From objects barely larger than mountains to monsters that could swallow our entire solar system. The edge of oblivion comes in sizes that defy human comprehension. Somewhere in our galaxy, right now, a massive star is dying. This star has burned for millions of years, not billions like our sun will, but millions. Massive stars live fast and die young. They burn through their nuclear fuel at a furious rate, converting hydrogen to helium, to carbon, to oxygen, to silicon, working their way up the periodic table in a desperate race against gravity. For all those millions of years, the outward pressure of nuclear fusion has balanced the inward pull of gravity. The star has existed in a delicate equilibrium, a controlled thermonuclear explosion held in check by its own weight. But now the fuel is running out. The core of the star has been converted to iron, and iron is the end of the line. Fusing iron doesn't release energy, it absorbs it. The nuclear furnace that has powered this star for eons is about to go dark. When it does, something catastrophic happens. Something violent beyond imagination. The core of the star, which might have been the size of Earth just moments before, suddenly has nothing holding it up. The outward pressure vanishes. Gravity, patient and relentless, finally wins. And in less than a second, the core collapses. Less than a second. Think about that. A structure the size of a planet containing more mass than our sun, collapsing to a sphere just tens of kilometers across. In less time than it takes to blink, matter is compressed to densities that dwarf anything found on Earth. Protons and electrons are forced together, combining to form neutrons. The temperature rises to hundreds of billions of degrees, hotter than the center of the sun by a factor of thousands. The outer layers of the star, suddenly unsupported, come crashing down. They slam into the collapsing core and bounce off, triggering a shock wave that races outward at tens of thousands of kilometers per second. This shock wave tears the star apart from the inside out. The outer layers are ejected into space in a titanic explosion that we call a supernova. For a few weeks, the dying star outshines this entire galaxy. A single star, briefly brighter than hundreds of billions of others combined. Ancient astronomers sometimes recorded these events, calling them guest stars, new lights that appeared in the sky and then faded away. They had no idea what they were witnessing. They had no concept of the violence involved. What happens to the core depends on how massive the original star was. For stars of intermediate mass, roughly between 8 and 25 times the mass of our Sun, the collapse is halted by neutron degeneracy pressure. The neutrons in the core, packed so tightly they're almost touching, resist further compression through quantum mechanical effects. The result is a neutron star, one of the strangest objects in the universe. Neutron stars are incredible. They pack roughly 1.5 solar masses into a sphere only about 20 kilometers across. That's the mass of the Sun compressed into something the size of a city. A teaspoon of neutron star material would weigh about 6 billion tons on Earth. You couldn't lift it. It would punch through the floor, through the foundation, through the crust of the Earth, and sink toward the core. Neutron stars spin incredibly fast. When the core collapses, like a figure skater pulling in their arms, it spins up. Some neutron stars rotate hundreds of times per second. Their magnetic fields are trillions of times stronger than Earth's. They emit beams of radiation from their poles, and if those beams happen to sweep past Earth as the star rotates, we see pulses of light. We call these pulsars. But neutron stars have a limit. The maximum mass a neutron star can have is somewhere between 2 and 3 times the mass of the Sun. This is called the Tolman-Oppenheimer-Volkoff limit, named after the physicists who calculated it. Beyond this mass, not even neutron degeneracy pressure can resist gravity. For stars more massive than about 25 solar masses, the core that remains after the supernova exceeds this limit. There's nothing to stop the collapse. No pressure, no force, no physical process known to science can halt gravity's final victory. The matter keeps shrinking. It passes the density of neutron stars. It keeps going. It shrinks past the size of cities, past the size of mountains, past the size of buildings, past the size of people. It shrinks past the size of atoms, past the size of atomic nuclei. And then it crosses the Schwarzschild radius. An event horizon forms, a boundary in space-time from which nothing can escape. The collapsing matter is now hidden behind this boundary forever. It can never send any signal to the outside universe. As far as the rest of reality is concerned, it has ceased to exist. What remains is a stellar black hole, a city-sized monster born in the death throes of a giant star. Consider the size of these objects, because understanding their scale is crucial to understanding how terrifying they really are. A typical stellar black hole has a mass between about 5 and 100 times the mass of our Sun. Most fall in the range of 10 to 30 solar masses. Remember, the Schwarzschild radius is directly proportional to mass. For every solar mass, you get about 3 kilometers of Schwarzschild radius. So for a black hole with 10 times the Sun's mass, the Schwarzschild radius is about 30 kilometers. The diameter of the event horizon is about 60 kilometers. 60 kilometers. Let that sink in. Manhattan Island is about 21 kilometers long. The entire island of Manhattan, with all its skyscrapers and millions of people, would fit inside the event horizon of a 10 solar mass black hole 3 times over. New York City, from the northern tip of the Bronx to the southern edge of Staten Island, spans about 50 kilometers. A stellar black hole could swallow all 5 boroughs. London, one of the world's largest cities, spans roughly 60 kilometers at its widest point. The event horizon of a modest stellar black hole is comparable in size to London. You could place the entire city from Heathrow to Greenwich inside the point of no return. For a black hole with 30 solar masses, the Schwarzschild radius is about 90 kilometers. The diameter is 180 kilometers. That's roughly the distance from Boston to Providence, from Paris to Reims, from San Francisco to Monterey. For a black hole with 50 solar masses, the Schwarzschild radius is about 150 kilometers. The event horizon diameter is 300 kilometers. That's the distance from Los Angeles to San Diego, from London to Birmingham, from New York to Washington, D.C. Still tiny by cosmic standards. Still barely a dot compared to planetary scales. The Earth has a diameter of about 12,700 kilometers. Even a 50 solar mass black hole's event horizon is less than 3% the width of Earth. Jupiter's diameter is about 140,000 kilometers. A stellar black hole is a speck compared to Jupiter, and yet, these city-sized regions of space-time contain masses equal to tens of suns. All that material, all those billions of billions of billions of tons, compressed into a space you could drive across in a few hours if there were a road. The concentration of mass is so extreme that our normal concepts of matter break down entirely. Let me tell you about some specific stellar black holes that astronomers have studied. These are real objects, observed and measured, lurking in the darkness of our galaxy. Cygnus X1 was the first black hole candidate to be widely accepted by the scientific community. Its story begins in 1964 when a rocket carrying X-ray detectors was launched to survey the sky. The detectors found a powerful source of X-rays in the constellation Cygnus, the Swan. This source was designated Cygnus X1, the first X-ray source discovered in that constellation. Further observations revealed something strange. Cygnus X1 appeared to be associated with a visible star, a blue supergiant called HDE 200, 26,868. This star was wobbling, as if being tugged by an invisible companion. By measuring the wobble, astronomers could calculate the mass of the invisible object. The result was startling. The invisible companion had a mass of about 21 times the mass of the Sun. It was far too massive to be a white dwarf or a neutron star. The only explanation that fit the observations was a black hole. Cygnus X1 is located about 6,000 light-years from Earth. Its Schwarzschild radius is roughly 63 kilometers, giving it an event horizon diameter of about 126 kilometers. Gas from the blue supergiant companion is continuously falling toward the black hole, forming a swirling disk of material called an accretion disk. As the gas spirals inward, friction heats it to millions of degrees. This superheated gas emits the powerful X-rays that first caught astronomers' attention. The accretion disk around Cygnus X1 is a violent place. Gas swirls around the black hole at a significant fraction of the speed of light. Magnetic fields twist and snap, accelerating particles to tremendous energies. Jets of matter shoot out along the black hole's rotation axis at nearly light speed, carrying energy thousands of light years into space. All of this chaos, all of this violence, surrounds an event horizon you could jog across in a morning. V404 Cygni is another well-studied stellar black hole, also located in the constellation Cygnus. It sits about 7,800 light-years from Earth. With a mass of about 9 times the Sun, it has a Schwarzschild radius of roughly 27 kilometers and an event horizon diameter of about 54 kilometers. Smaller than Cygnus X1, but still a monster. V404 Cygni is normally quiet. The black hole drifts through space, slowly consuming material from its companion star at a modest rate. But occasionally something changes. Material builds up in the accretion disk until it becomes unstable. Then the black hole goes into outburst. In June of 2015, V404 Cygni experienced its first major outburst in 26 years. The black hole suddenly brightened by a factor of thousands as it consumed a surge of material. The outburst was so intense it was detected across the entire electromagnetic spectrum, from radio waves to gamma rays. Amateur astronomers with backyard telescopes could see the flickering light of gas falling into a black hole nearly 8,000 light-years away. The outburst lasted several weeks, with the black hole's brightness fluctuating wildly, sometimes changing by a factor of 2 in just minutes. These fluctuations told astronomers about the chaotic conditions in the accretion disk, where clumps of gas were falling in at irregular intervals. Each time a clump crossed the event horizon, there was a burst of radiation. Then darkness as the material vanished forever. Then there are the black holes we've detected, not through light, but through the ripples they make in space-time itself. On September 14th, 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected something historic. For the first time in human history, we directly observed gravitational waves, ripples in the fabric of space-time predicted by Einstein a century earlier. The source of these waves was designated GW150914, named for the date of detection. And what LIGO detected was astounding. 2 black holes spiraling toward each other, finally merging in a cataclysmic collision. The 2 black holes had masses of about 36 and 29 times the mass of the Sun. They had been orbiting each other for eons, gradually spiraling closer as gravitational waves carried away their orbital energy. In the final moments before merger, they were whipping around each other at nearly half the speed of light, completing orbits in a fraction of a second. Then they collided. 2 event horizons touched and merged. 2 singularities became one. In a fraction of a second, a new black hole was born with a mass of about 62 solar masses. Wait, 36 plus 29 is 65. Where did the missing 3 solar masses go? They were converted into energy. Pure energy, released as gravitational waves that rippled outward at the speed of light. 3 solar masses, about 6 times 10 to the 30th kilograms, converted to energy according to Einstein's famous equation E equals mc squared. The energy released was staggering. In the final fraction of a second before the merger, those 2 black holes radiated more energy than all the stars in the observable universe combined. For that brief instant, the merger was the most powerful event happening anywhere in the cosmos. The gravitational waves it produced traveled across 1.3 billion light-years of space to reach Earth, where they stretched and squeezed our planet by a distance smaller than the width of a proton. And the result of this cosmic cataclysm? A black hole with a Schwarzschild radius of about 186 kilometers. An event horizon roughly 370 kilometers in diameter. A region of no return smaller than many countries, containing 62 times the mass of our Sun. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. Each one tells us more about these city-sized monsters. We've found black holes larger than we expected from stellar evolution alone. We found pairs that shouldn't exist according to our models. The gravitational wave universe has opened a new window on black holes, and what we're seeing is sometimes surprising. Astronomers estimate that the Milky Way contains somewhere between 100 million and 1 billion stellar black holes. Most of them are dormant, floating alone in the void, invisible unless something happens to fall near them. They're the silent remnants of massive stars that died long ago, drifting through the galaxy like ghosts. Some are in binary systems, slowly consuming their companion stars. Others are isolated, occasionally passing through clouds of interstellar gas that briefly light up their accretion disks. A few are in crowded stellar environments where they might encounter other black holes and eventually merge. Right now, as you listen to this, millions of black holes are orbiting through our galaxy. Some are thousands of light years away. Some might be much closer, and every single one of them is a point of no return. A city-sized boundary where the laws of physics as we understand them begin to break down. Now, let me describe what would happen if you approach one of these monsters. Not in theory, but as best as physics can predict. Imagine you're in a spacecraft falling toward a stellar black hole. Let's say it's a 10 solar mass black hole with an event horizon about 60 kilometers in diameter. At first, from a distance, the black hole would be almost invisible against the backdrop of stars. Black holes don't emit light. They're defined by the absence of light. They're darkness against darkness. You might not see the black hole itself at all. What you would see is the effect the black hole has on the light around it. Stars behind the black hole would appear to shift and distort as their light bends around the intense gravitational field. This effect, called gravitational lensing, would make the background stars appear to dance and shimmer as you moved. Some stars would appear stretched into arcs. Others would appear duplicated, their light following multiple paths around the black hole. As you get closer, the distortion becomes more dramatic. The black hole begins to dominate your view. Stars on the opposite side of the black hole appear stretched into complete rings, Einstein rings, as their light wraps entirely around the event horizon. The black hole's photon sphere, the region where light can orbit before eventually spiraling in or escaping, creates a bright ring against the darkness. If the black hole is actively feeding on nearby material, you would see the accretion disk. This is perhaps the most spectacular sight in the universe. A disk of superheated gas and dust, glowing at millions of degrees, swirling around the event horizon at nearly the speed of light. The disk would be asymmetric, appearing brighter on one side due to relativistic effects. The side rotating toward you would be blue shifted and brightened. The side rotating away would be red shifted and dimmed. The inner edge of the accretion disk would glow with intense radiation, primarily X-rays and gamma rays. The whole structure would be a blazing inferno of superheated plasma, outshining entire stars as matter converts its gravitational energy to light before vanishing forever. But the beauty is deceiving. As you approach, something sinister is happening to your body. Tidal forces are building. Gravity obeys an inverse square law. The closer you are to a massive object, the stronger the gravitational pull. But this means that different parts of your body, at different distances from the black hole, experience different gravitational pulls. If you're falling feet first toward the black hole, your feet are closer to the center of mass than your head. They experience a stronger gravitational pull. This difference in pull stretches you lengthwise. At the same time, gravity is pulling all parts of you toward the center of the black hole, which compresses you sideways. You're being stretched like taffy, pulled longer and squeezed narrower. For a stellar black hole, these tidal forces become lethal long before you reach the event horizon. The gradient of gravity is steep. The difference in pull between your head and feet increases rapidly as you approach. Physicists have a technical term for what happens next: spaghettification. You would be stretched thinner and thinner as you fell. At some point, the tidal forces would exceed the tensile strength of your body. Your spine would separate. Your limbs would be pulled off. You would be torn apart, not by any impact or collision, but simply by the gradient of gravity. But the destruction wouldn't stop there. The tidal forces would keep increasing. Your separated body parts would themselves be stretched and torn. Your cells would be pulled apart. Your molecules would be ripped into atoms. Your atoms would be stretched into thin streams of subatomic particles, spiraling down toward the event horizon. Long before you reach the event horizon of a stellar black hole, you would be reduced to a thin stream of plasma, a ribbon of matter stretched across thousands of kilometers, glowing as it heated up, then vanishing forever as it crossed the point of no return. For a stellar black hole with an event horizon the size of a city, spaghettification begins when you're still thousands of kilometers away. There's no gentle approach. There's no way to hover near the event horizon and peer in. The tidal forces would kill you long before you got close enough to see anything interesting. This is one of the cruel ironies of stellar black holes. They're small enough that their tidal forces are lethal at the event horizon, which means that no observer could survive to cross the boundary and experience what lies beyond. The event horizon is real, but no human could ever witness it directly. But here's something remarkable that reveals the strange relationship between mass and violence in black hole physics. The deadliness of tidal forces actually decreases as black holes get larger. This seems counterintuitive. Surely a bigger black hole with more mass should be more deadly. But tidal forces depend on the gradient of gravity, how quickly the gravitational pull changes over distance. For a larger black hole with a more distant event horizon, that gradient is gentler. Think of it this way. For a small black hole, you're very close to the singularity when you cross the event horizon. The gravity is changing rapidly over short distances. The tidal forces are intense. For a supermassive black hole, the event horizon is millions of kilometers from the singularity. You're relatively far from the source of gravity when you cross the boundary. The tidal forces at the horizon are much weaker. For stellar black holes, the tidal forces at the event horizon are catastrophic, but for supermassive black holes, the event horizon is so large that a human could cross it without being immediately torn apart. You would still be doomed, of course. Once inside the event horizon, you cannot escape, and the singularity awaits, but you would have some time to experience the interior of a black hole before the end. This brings us to one of the strangest aspects of falling into a black hole, the perspective paradox. From your perspective, falling into the black hole, everything seems normal. Your local physics appears unchanged. Your watch keeps ticking. Your heart keeps beating. You don't feel the event horizon. There's no sign, no barrier, no flash of light marking the boundary. You would simply find, after crossing, that no matter how hard you tried, you could never send a signal back out. You've crossed a one-way door in space-time, but from the perspective of someone watching you from outside, something completely different happens. They see you slow down as you approach the event horizon. They see your movements become sluggish, then glacial. They see light from your body redshift, stretching to longer and longer wavelengths. They see you grow dimmer and redder, frozen at the boundary, never quite crossing. From the outside observer's perspective, you never enter the black hole. You're frozen at the event horizon forever, a dim red ghost at the edge of oblivion. Both perspectives are valid. Both are correct according to the physics. Time runs at different rates, depending on where you are in a gravitational field. What you experience as crossing the horizon in a finite time appears to outside observers as an infinite approach that never completes. This paradox has deep implications for physics. It raises questions about what information means in a universe with black holes. It connects to some of the deepest problems in theoretical physics, including the nature of quantum gravity and the fate of information that falls into black holes. Stellar black. Holes are city-sized monsters, the collapsed corpses of giant stars scattered throughout our galaxy. They warp space-time so severely that light cannot escape. They mark boundaries where our normal understanding of physics breaks down. They're surrounded by accretion disks of superheated matter and regions where tidal forces would tear anything apart. And there are hundreds of millions of them in the Milky Way alone. But as impressive and terrifying as stellar black holes are, they're actually quite small by black hole standards. They're the lightweights, the minor players. Because at the centers of galaxies, there are black holes that make stellar black holes look like grains of sand on a beach. Black holes whose event horizons span not kilometers, but millions of kilometers. Black holes that don't just consume stars, but orchestrate the motions of millions of them. The mathematics of stellar black holes reveals something profound about the relationship between mass and the Schwarzschild radius. The relationship is beautifully simple. Double the mass, and you double the Schwarzschild radius. Triple the mass, triple the radius. It's perfectly linear. This has a strange consequence. As black holes get more massive, their average density actually decreases. A 10 solar mass black hole with a Schwarzschild radius of 30 kilometers has an average density comparable to the density of nuclear matter, about 10 to the 14th grams per cubic centimeter. That's unimaginably dense. A thimbleful would weigh billions of tons, but a black hole with a billion solar masses would have an average density less than that of water, less than 1 gram per cubic centimeter. If you divided the mass by the volume enclosed within the event horizon, you get a density that could float. This seems deeply counterintuitive. Black holes are supposed to be the densest objects in the universe, and they are at the singularity. But the average density spread over the entire volume within the event horizon decreases as black holes grow. The reason is geometric. The volume enclosed within the event horizon increases as the cube of the radius, while the mass only increases linearly with radius. As black holes get bigger, their event horizons encompass more and more empty space. Space that contains no matter, just curved spacetime. This has profound implications for how supermassive black holes form and behave. It means they don't require the extreme compressions of stellar collapse. It means their event horizons can be surprisingly gentle places, at least compared to stellar black holes. And it means the largest black holes in the universe have event horizons so vast they could swallow entire solar systems without any increase in tidal forces that you'd notice. But before we get to those cosmic leviathans, those monsters that span hundreds of billions of kilometers, let's talk about something closer to home, something lurking in the darkness at the center of our own galaxy. 26,000 light years away, hidden behind clouds of gas and dust, there's a black hole 4 million times more massive than the Sun. Its event horizon spans millions of kilometers. Stars orbit it at thousands of kilometers per second. It's called Sagittarius A star. And it's been there, waiting, for as long as our galaxy has existed. Look up at the night sky on a clear summer evening, and you'll see a pale band of light stretching from horizon to horizon. This is the Milky Way, our home galaxy, seen edge on from our position within it. For thousands of years, humans gazed at this celestial river and wondered what it was. Ancient Greeks thought it was milk, spilled from the breast of the goddess Hera. The Maori of New Zealand saw it as a great canoe. Chinese astronomers called it the Silver River. We now know its light from hundreds of billions of stars, so distant and so numerous that their individual points blur into a continuous glow. And somewhere in that glow, in the direction of the constellation Sagittarius, lies the center of our galaxy, the heart of the Milky Way. For most of human history, we didn't know our galaxy had a center. We didn't even know we were in a galaxy. The stars seemed to be scattered randomly across the sky, points of light without any larger structure or organization. It wasn't until the early 20th century that astronomers began to map the Milky Way's true shape. A vast spiral of stars stretching 100,000 light years across. And to locate our position within it, about 2/3 of the way out from the center. And it wasn't until the 1970s that we discovered something extraordinary lurking at the very center. Something massive, something dark, something that would challenge our understanding of the universe itself. The story begins with radio astronomers. In the decades after World War II, astronomers learned to build radio telescopes, instruments that could detect radio waves instead of visible light. Radio waves can penetrate the clouds of gas and dust that block visible light from the galactic center, allowing us to peer into regions that optical telescopes cannot see. In 1974, astronomers Bruce Ballack and Robert Brown were using the National Radio Astronomy Observatory's interferometer in Green Bank, West Virginia. They were surveying the region near the galactic center, mapping sources of radio emission, and they found something unusual. There was a powerful and compact radio source right at the center of the galaxy in the direction of the constellation Sagittarius. They called it Sagittarius A, designating it as the brightest radio source in that region of the sky. Further observations with better instruments revealed that within Sagittarius A, there was an even more compact source. This inner source was incredibly small by astronomical standards, no larger than our solar system, yet it was emitting intense radio waves. They designated this source at Sagittarius a star, with the asterisk indicating its point-like stellar nature. What could be so small, yet so powerful? What kind of object could emit such intense radiation from such a tiny region of space? The answer would take decades to confirm, but the suspicions began almost immediately. There was really only one type of object that fit the observations: a black hole. Not just any black hole, but a supermassive one, millions of times more massive than our sun. The definitive proof came from observations of stars near the galactic center. In the 1990s, two teams of astronomers began an ambitious project. They would track the motions of stars orbiting close to Sagittarius, a star, mapping their paths year after year, decade after decade. If there was a massive object at the center, the stars would orbit it, and by measuring their orbits, astronomers could calculate the mass of the central object. This was incredibly difficult work. The galactic center is 26,000 light-years away, obscured by vast clouds of dust and crowded with millions of stars. Picking out individual stars and tracking their motions required the most advanced telescopes on Earth, equipped with adaptive optic systems that could compensate for the blurring caused by Earth's atmosphere. One team was led by Andrea Ghez at the University of California, Los Angeles. She used the Keck telescopes in Hawaii, the largest optical telescopes in the world at that time, with mirrors 10 meters across. The other team was led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany. He used the Very Large Telescope in Chile, operated by the European Southern Observatory. For over 2 decades, both teams watched and waited, measuring the positions of stars near the galactic center with increasing precision. And what they found was remarkable. Stars near Sagittarius, a star were moving incredibly fast, not just fast by astronomical standards, but fast by any standard. Some stars were moving at thousands of kilometers per second. To put that in perspective, the space shuttle orbited Earth at about 8 kilometers per second. These stars were moving hundreds of times faster. One star in particular captured everyone's attention. Designated S2, this star was observed completing a full orbit around Sagittarius A star in just 16 years. Think about what that means. In our solar system, Mercury is the fastest planet, whipping around the sun in just 88 days at a speed of about 47 kilometers per second. Pluto, the slowest, takes 248 years to complete one orbit. The sun itself takes about 230 million years to orbit the galactic center. But S2 completes its orbit around Sagittarius A star in just 16 years. At its closest approach, called periapsis, S2 passes within about 17 light hours of the central object, traveling at speeds exceeding 5,000 kilometers per second. That's nearly 2% of the speed of light. A star, a massive ball of plasma similar to our sun, moving at 2% of light speed. For a star to orbit that fast without flying off into space, the central object must be incredibly massive. Gravity is what keeps objects in orbit. The more massive the central object, the faster something can orbit at a given distance. By carefully tracking S2 and dozens of other stars near Sagittarius A star, both teams calculated the mass of the central object. The result was staggering. Approximately 4 million times the mass of our sun, all concentrated in a region smaller than our solar system. Smaller, in fact, than the orbit of Neptune around the sun. There is only one type of object that could be that massive and that compact. A black hole. A supermassive black hole. The work of Ghez and Genzel was so important, so fundamental to our understanding of the universe, that they shared the 2020 Nobel Prize in Physics. The Nobel Committee recognized them for proving the existence of a supermassive black hole at the center of the Milky Way. It was one of the most significant astronomical discoveries of the century. Let me calculate the Schwarzschild radius of Sagittarius A star, so you can understand the true scale of this monster. We know the formula. The Schwarzschild radius equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For the Sun, this gives about 3 kilometers. For Sagittarius A star, with 4 million times the Sun's mass, we simply multiply by 4 million. The result is approximately 12 million kilometers. That's the radius of the event horizon. The diameter from one side of the point of no return to the other is about 24 million kilometers. Think about what that means. The Sun has a radius of about 696,000 kilometers. So the event horizon of Sagittarius A star is about 17 times larger than the Sun's radius. If you could somehow place Sagittarius A star where the Sun is, its event horizon would extend outward for 12 million kilometers in every direction. That's a sphere of no return nearly twice as wide as the Sun. Mercury, the innermost planet, orbits at an average distance of about 58 million kilometers from the Sun. So Sagittarius A star's event horizon, at 12 million kilometers radius, is about 1/5 of the way from the Sun to Mercury's orbit. The inner solar system would still be outside the event horizon, but not by much. Mercury would orbit at only about 4.5 times the radius of the event horizon. Venus, at 108 million kilometers, would be about 9 times the radius of the event horizon. Earth, at 150 million kilometers, would be about 12.5 times the radius. We will be safe, but the black hole would dominate our sky, a vast dark sphere nearly half the apparent size of the Sun. This is genuinely enormous by stellar black hole standards. Remember, a typical stellar black hole has an event horizon measured in tens of kilometers, a city-sized sphere of darkness. Sagittarius, a star's event horizon is millions of kilometers across. It's about 400,000 times larger than a typical stellar black hole. 400,000 times. If a stellar black hole's event horizon is the size of a city, Sagittarius A star's event horizon is the size of a small planet's orbit. But here's something that might surprise you. In the context of supermassive black holes across the universe, Sagittarius A star is actually relatively modest. It's on the smaller end of the supermassive scale. Many galaxies harbor black holes that are hundreds or thousands of times more massive than Sagittarius A star. Some contain black holes billions of times the mass of the Sun, not millions. Sagittarius A star at 4 million solar masses is a lightweight among supermassive black holes. Still, 4 million solar masses is almost impossible to truly comprehend. Here's another way to grasp that amount of mass. The mass of Sagittarius A star is about 8 times 10 to the 36th kilograms. That's an 8 followed by 36 zeros. If you try to write this number out in full, with each digit taking 1 millimeter of space, the number would stretch for 37 meters. The mass of Sagittarius A star, written as a simple integer, would be longer than a school bus. The Sun contains about 330,000 times more mass than Earth. It dominates our solar system, containing 99.8% of all the mass in the system. Everything else, all the planets, moons, asteroids, and comets, is less than a rounding error. Sagittarius A star contains about 4 million times more mass than the Sun. So it contains about 1.3 trillion times more mass than Earth, 1,300,000,000,000,000 Earths. If you could somehow gather 1,300,000,000,000,000 Earth mass planets and compress them into a single object, you would have something with the mass of Sagittarius A star. And all of that mass is concentrated within an event horizon 24 million kilometers across. A region of space-time from which nothing can escape, a cosmic trap at the heart of our galaxy. In 2019, the world saw something that had once seemed impossible. We saw a black hole. The Event Horizon Telescope is not a single instrument. It's a network of radio telescopes scattered across the globe, from Hawaii to Arizona to Spain, to Chile to the South Pole. By coordinating their observations and combining their data, these telescopes can function as a single instrument with an effective diameter equal to the diameter of Earth itself. This gives the Event Horizon Telescope the highest resolution of any telescope ever built, capable of seeing details as small as the event horizons of supermassive black holes. In April of 2017, the Event Horizon Telescope observed 2 targets. One was Sagittarius A star at the center of our galaxy. The other was M87 star, the supermassive black hole at the center of the giant elliptical galaxy M87, about 55 million light-years away. It took 2 years to process the data. The amount of information was so vast that it couldn't be transmitted over the internet. Hard drives had to be physically shipped from the South Pole to processing centers. Sophisticated algorithms had to combine observations from telescopes on different continents, accounting for the rotation of the Earth and the minute differences in timing between observatories. In April of 2019, the Event Horizon Telescope collaboration released their first image, but it wasn't Sagittarius A star. It was M87 star. The image showed a bright ring of light surrounding a dark central shadow. The ring was glowing gas and dust, orbiting just outside the event horizon, heated to billions of degrees, emitting radio waves that the Event Horizon Telescope could detect. The dark center was the shadow of the black hole itself, the region from which no light could escape, It was the first direct visual evidence of an event horizon. The first time humanity had seen the edge of a black hole. M87 star has a mass of about 6.5 billion solar masses, more than 1,000 times the mass of Sagittarius, a star. Its event horizon is correspondingly larger, about 40 billion kilometers in diameter. Despite being 1,000 times farther away than Sagittarius A star, its larger size meant that its event horizon spans a similar angle in the sky, making it equally good as an imaging target. But the world wanted to see our black hole, the one at the center of our own galaxy. In May of 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A star. The image is hauntingly beautiful. A bright, somewhat lumpy ring of orange and yellow surrounds a dark central void. The ring is glowing gas, superheated material orbiting the black hole at nearly the speed of light, emitting radio waves that travel 26,000 light years to reach our telescopes. The dark center is the shadow of Sagittarius, a star, the region where space-time is so curved that all light falls inward, never to escape. Imaging Sagittarius A star was actually harder than imaging M87 star, despite Sagittarius A star being much closer. The reason is the difference in mass. Sagittarius A star is about 1,600 times less massive than M87 star. This means that matter orbits much faster around Sagittarius A star. Remember, smaller black holes have stronger gravitational gradients. The inner edge of the accretion disk around M87 star takes days to weeks to complete an orbit. The glowing gas has time to arrange itself into relatively stable patterns. Around Sagittarius, a star, gas at the inner edge of the accretion disk completes an orbit in about 4 minutes. The appearance of the glowing ring changes significantly during a single night of observation. Trying to image Sagittarius A star is like trying to photograph a car by taking a long exposure while the car races around a track. The image blurs. The Event Horizon Telescope team had to develop new techniques to handle this challenge. They couldn't simply combine all their data into a single image. Instead, they had to account for the changing appearance of the source, building up an average picture that captured the stable features while averaging out the rapid fluctuations. The result confirms what astronomers had already deduced from the orbits of stars. There really is a supermassive black hole at the center of our galaxy. We can see its shadow, we can measure its size, and remarkably, the size matches the predictions of general relativity with extraordinary precision. Einstein's theory, developed over a century ago, predicted exactly how large the shadow of a 4 million solar mass black hole should appear. The Event Horizon Telescope measured that shadow. The agreement is almost perfect. Once again, Einstein was right. Now, should we be worried about this monster at the center of our galaxy? The short answer is no. Sagittarius. A star poses no threat to Earth whatsoever. The center of the Milky Way is about 26,000 light years from Earth. Consider that distance for a moment. Light travels at 300,000 kilometers per second. That's fast enough to circle the Earth more than 7 times in a single second. Light from the moon reaches us in about 1.3 seconds. Light from the sun takes about 8 minutes. Light from the edge of the solar system, from the Kuiper belt where Pluto orbits, takes about 5.5 hours. Light from Sagittarius, a star, takes 26,000 years. When the light that reaches our telescopes tonight left the galactic center, modern humans were just beginning to spread across Europe and Asia. We shared the planet with the Neanderthals. We hadn't yet developed agriculture, or writing, or cities. We lived in small bands of hunter-gatherers, following animal herds across Ice Age landscapes. 26,000 years of human history have passed while that light traveled towards us. At this enormous distance, Sagittarius A star has no direct gravitational influence on Earth. Gravity weakens with the square of distance. At 26,000 light years, the gravitational pull of a 4 million solar mass black hole is utterly negligible. You feel a stronger gravitational pull from the book on your nightstand than from Sagittarius A star. The black hole's gravitational influence extends only a few light years from its event horizon. Stars within that region orbit the black hole directly, their paths determined primarily by its gravity. But beyond that, stars orbit the galactic center just as they would if the same 4 million solar masses were spread out into ordinary stars instead of being concentrated in a black hole. In fact, the Sun and the entire solar system are orbiting Sagittarius A star right now. We're moving at about 230 kilometers per second around the galactic center, along with all the other stars in our neighborhood. At this speed, it takes about 230 million years to complete one orbit, a period sometimes called a galactic year. The last time the Sun was at this point in its orbit, dinosaurs hadn't evolved yet. The Permian period was ending. Life was recovering from the greatest mass extinction in Earth's history. 230 million years from now, who knows what will exist on Earth? But the solar system will return to this point in the galaxy, having completed another orbit around Sagittarius A star. But what would happen if you could actually travel to Sagittarius A star? What would you experience if you approach this cosmic monster? With current technology, the journey is impossible. Even at the speed of light, it would take 26,000 years. At the speed of our fastest spacecraft, traveling at about 17 kilometers per second, it would take over 400 million years. The Sun will have burned out long before any craft launched today could reach the galactic center. But let's imagine you could somehow make the journey. What would you see? As you approach the center of the galaxy, the density of stars would increase dramatically. In our solar neighborhood, the nearest star is about 4 light years away. Near the galactic center, stars are packed thousands of times more densely. If Earth orbited a star near Sagittarius A star, our night sky would blaze with thousands of stars, as bright as Venus appears to us. Thousands more as bright as Jupiter. The Milky Way band would be overwhelmingly bright. There would be no true darkness. As you got closer to Sagittarius, a star itself, you would begin to see its effects. Stars orbiting close to the black hole would be visibly moving, racing around their orbits at thousands of kilometers per second. You might see S2 completing its 16-year orbit, moving perceptibly against the background of more distant stars. The space-time around you would be noticeably warped, causing background stars to shift and distort. Sagittarius A star is currently not very active. It's what astronomers call a quiescent black hole. The rate at which material is falling into it is relatively low, so there's no bright accretion disk, no powerful jets. The black hole sits quietly at the center of the galaxy, occasionally swallowing a small amount of gas or dust, but not putting on much of a show. But sometimes, Sagittarius A star flares. Observations have caught it brightening by factors of tens or even hundreds for brief periods, probably when clumps of gas fall toward the event horizon and heat up, before vanishing. If you approach during one of these flares, You might see a brilliant ring of glowing gas around the dark shadow of the event horizon. Now you get close, really close. Within the radius of Mercury's orbit, if the Sun were replaced by Sagittarius A star, you're approaching the event horizon, that 24 million kilometer sphere of no return. Here's where something remarkable happens, or rather, doesn't happen. The tidal forces at the event horizon of Sagittarius A star are survivable. Remember what we learned about stellar black holes? The tidal forces that would spaghettify you depend on the gradient of gravity, how quickly the pull changes across your body. For a larger black hole with a more distant event horizon, that gradient is gentler. The mathematics is counterintuitive but inescapable. Tidal forces at the event horizon actually decrease as black holes grow larger. For Sagittarius A star, a human crossing the event horizon would experience tidal forces, roughly equivalent to being stretched by a fraction of Earth's gravity. Uncomfortable perhaps, but not deadly. You could survive crossing the event horizon of Sagittarius A star, but survival is temporary. Once inside, there is no escape. All paths lead inward. The singularity awaits. How long do you have? For Sagittarius, a star, the time from crossing the event horizon to reaching the singularity is approximately 1 minute. 60 seconds of existence inside a black hole, falling through progressively more warped space-time, watching the universe outside appear to speed up due to time dilation effects, knowing that no signal you send will ever reach the outside world. Then you meet the singularity, and there, our physics ends. General relativity predicts infinite density, infinite curvature, but physicists believe these infinities are a sign that the theory breaks down. What actually happens at the singularity, what lies beyond that final boundary, remains one of the deepest mysteries in all of science. Sagittarius. A star guards this mystery at the heart of our galaxy. A 4 million solar mass black hole with an event horizon 24 million kilometers across, orbited by stars moving at thousands of kilometers per second. Photographed by telescopes spanning the globe, proven to exist beyond any doubt. It's been there for billions of years. It will be there for billions more. The heart of darkness at the center of the Milky Way. But as massive as Sagittarius A star is, as incomprehensibly large as its event horizon seems, there are black holes out there that dwarf it completely. Black holes so large that Sagittarius A star would be a tiny speck compared to their event horizons. Black holes whose points of no return are larger than our entire solar system. These are the ultramassive black holes, and they represent the true upper limit of how large these cosmic monsters can grow. We have journeyed from the trenches of World War I, where Karl Schwarzschild first calculated the radius of no return, through the city-sized stellar black holes that litter our galaxy like cosmic landmines, to the 4 million solar mass monster that lurks at the heart of the Milky Way. We have seen event horizons grow from tens of kilometers to millions of kilometers. We have watched the scale of these cosmic abysses expand beyond anything in human experience. But we haven't reached the end, not even close, because out there, in the distant reaches of the observable universe, there are black holes that make Sagittarius a star look tiny. Black holes so massive, so incomprehensibly large, that their event horizons dwarf not just planets, not just stars, but our entire solar system. Everything we know, everything we've ever explored, every world we've ever dreamed of visiting, could fit inside the point of no return of these cosmic leviathans with room to spare. These are the ultramassive black holes, and they represent the true upper limit of how large these monsters can grow. Let me introduce you to TON 618. TON 618 is a quasar, one of the most luminous objects in the known universe. The name comes from the Tonantzintla Observatory in Mexico, where it was first catalogued in the 1950s as part of a survey of blue objects in the sky. At the time, astronomers didn't know what they were looking at. It appeared to be a star, a single point of blue light, unremarkable except for its unusual colour. But TON 618 is not a star. It's not even in our galaxy. TON 618 is located approximately 10.4 billion light years from Earth. Let that distance sink in for a moment. The light we see from TON 618 today left its source when the universe was only about 3.4 billion years old. The universe is currently about 13.8 billion years old. The light from TON 618 has been travelling towards us for more than 75% of the age of the cosmos. When that light began its journey, the sun didn't exist. Earth didn't exist. The solar system was still a cloud of gas and dust, not yet collapsed into a star and its retinue of planets. The light from TON 618 is older than everything we know. And what is the source of this ancient light? What kind of object can shine brightly enough to be seen across 10 billion light years of space? The answer took decades to uncover, and the journey to understanding is one of the strangest detective stories in the history of astronomy. In the 1950s and 60s, radio astronomers began detecting powerful sources of radio waves scattered across the sky. When they pointed optical telescopes at these radio sources, they often found what appeared to be ordinary stars, blue points of light, unremarkable except for their unusual brightness at radio wavelengths. But when astronomers analyzed the light from these objects, something was wrong. The spectral lines, the fingerprints of chemical elements that astronomers use to identify what things are made of, were shifted to wavelengths that didn't match any known element. The spectra made no sense. In 1963, astronomer Martin Schmidt had a breakthrough. He realized the spectral lines weren't from unknown elements. They were from ordinary hydrogen, but shifted enormously toward the red end of the spectrum. This redshift meant the objects were moving away from us at tremendous speeds. And in an expanding universe, the faster something is receding, the farther away it must be. The implications were staggering. These quasi-stellar objects, quickly shortened to quasars, weren't nearby stars at all. They were the most distant objects ever observed, billions of light years away. And if they were that far away yet still visible, they had to be incredibly luminous. More luminous than entire galaxies. More luminous than anything astronomers had ever imagined. What could possibly produce such enormous energy from such a compact region? For years, astronomers struggled with this question. Nuclear fusion couldn't explain it. Chemical reactions couldn't explain it. Nothing in known physics seemed adequate. The answer we now know is gravity. Specifically, the gravitational energy released by matter falling into a supermassive black hole. As matter falls toward the black hole, it forms an accretion disk, a swirling maelstrom of superheated material that can reach temperatures of billions of degrees. This disk emits radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The energy output is staggering. TON 618's accretion disk outshines entire galaxies. It produces as much light as hundreds of trillions of suns. But the black hole itself is what truly defies comprehension. The black hole at the heart of TON 618 has a mass estimated at approximately 66 billion times the mass of our Sun. Let me say that again, more slowly, so it has time to register. 66 billion solar masses. 66 billion. That's 66,000 times more massive than Sagittarius A star. The black hole at the center of our galaxy, the 4 million solar mass monster that dominates the heart of the Milky Way, is a speck compared to TON 618. You could fit 16,500 Sagittarius A stars inside TON 618 and still have room for more. Let's calculate the Schwarzschild radius of this behemoth. We know the formula. The Schwarzschild radius equals approximately 3 kilometers for every solar mass. For 66 billion solar masses, we multiply 3 kilometers by 66 billion. The result is approximately 198 billion kilometers. 198 billion kilometers. That's the radius of the event horizon. The diameter, the distance from one side of the point of no return to the other, is approximately 396 billion kilometers. These numbers lose all meaning without comparison, so let's ground them in something familiar. Our solar system has a scale that most people find difficult to grasp. Earth orbits the Sun at a distance of about 150 million kilometers, a distance we call 1 astronomical unit. This is already far beyond human intuition. Light takes about 8 minutes to travel from the Sun to Earth. A car driving at highway speed would take about 170 years to cover the same distance. Mars orbits at about 228 million kilometers from the Sun. Jupiter about 778 million kilometers. Saturn at about 1.4 billion kilometers. Uranus at about 2.9 billion kilometers. Neptune, the outermost planet, orbits at about 4.5 billion kilometers from the Sun. Pluto, the famous dwarf planet at the edge of our traditional solar system, orbits at an average distance of about 5.9 billion kilometers. At its most distant point in its elliptical orbit, Pluto can be as far as 7.4 billion kilometers from the Sun. The Kuiper Belt, the ring of icy bodies beyond Neptune that includes Pluto, extends to about 50 astronomical units, or roughly 7.5 billion kilometers. Beyond that lies the scattered disk and eventually the Oort cloud, a vast spherical shell of comets that may extend to 100,000 astronomical units, or about 15 trillion kilometers. Now consider TON 618. Its event horizon has a radius of 198 billion kilometers. That's more than 26 times the distance from the Sun to Pluto. That's more than 13 times the distance to the outer edge of the Kuiper Belt. If you placed TON 618 where our Sun is, its event horizon would swallow Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. It would swallow the entire Kuiper Belt. It would extend far beyond any region we consider part of our solar system. Our entire solar system, every planet, every moon, every asteroid, every comet, everything we've ever studied or dreamed of exploring would fit inside the event horizon of TON 618, with enormous room to spare. Here's another comparison that might help. Light travels at approximately 300,000 kilometers per second. This is the fastest speed possible in the universe. Nothing can exceed it. Light is the cosmic speed limit. Light travels from the Sun to Earth in about 8 minutes. From the Sun to Jupiter takes about 43 minutes. From the Sun to Neptune takes about 4 hours. From the Sun to Pluto takes about 5.5 hours. How long would it take light to cross the diameter of TON 618's event horizon? 396 billion kilometers divided by 300,000 kilometers per second equals approximately 1,320,000 seconds. That's about 15.3 days. Light would need more than 2 weeks to cross from one side of this black hole's event horizon to the other. 2 weeks for light. Light, the fastest thing in existence, moving at 300,000 kilometers every second, would need 15 days to traverse this single object. A few more comparisons might drive this scale home. The Orion Nebula, one of the most famous objects in the night sky, is about 24 light-years across. TON 618's event horizon is about 15 light-days across. The black hole is smaller than the nebula, but not by as much as you might expect. A single object, a boundary of no return, spanning a significant fraction of a stellar nursery's width. Consider this. If you could somehow line up Earths from one side of TON 618's event horizon to the other, you would need about 31 million of them. 31 million Earths, touching edge to edge, to span the diameter of this one black hole. Or think about it in terms of the Sun. The Sun has a diameter of about 1.4 million kilometers. You could fit approximately 283,000 suns across the diameter of TON 618's event horizon. Nearly 300,000 suns lined up in a row to match the width of this single dark region. The numbers become meaningless after a while. The human brain simply cannot process scales this large. We evolved to understand the distance to the next watering hole, not the diameter of cosmic monsters. For comparison, light crosses the diameter of Sagittarius A star's event horizon in about 80 seconds. Light crosses the diameter of a stellar black hole's event horizon in less than a millisecond. TON 618 exists on a scale that makes every other black hole we've discussed seem trivial. And all of that space, all 396 billion kilometers of diameter, contains nothing but darkness and warped spacetime. Once inside, nothing comes out. The 66 billion solar masses worth of matter that fell into this black hole over billions of years is gone forever, hidden behind an event horizon larger than our entire solar system. But TON 618 is not alone. There are other ultramassive black holes scattered throughout the observable universe, each one a cosmic leviathan of incomprehensible scale. Holmberg 15. A star sits at the center of Holmberg 15A, a giant elliptical galaxy about 700 million light-years from Earth. This black hole has an estimated mass of approximately 40 billion solar masses, giving it a Schwarzschild radius of roughly 120 billion kilometers. Its event horizon diameter is about 240 billion kilometers, still large enough to swallow our entire solar system out to the Kuiper Belt with room to spare. Holmberg 15A is interesting because of its environment. The galaxy that hosts it has an unusually large core, a region near the center that is depleted of stars. Astronomers believe this depletion was caused by the black hole itself, ejecting stars through gravitational interactions as it grew to its current enormous size. The black hole has literally sculpted its host galaxy, carving out a void in the stellar population that surrounds it. Then there's the black hole in IC 1101, sometimes called the largest known black hole. IC 1101 is a supergiant elliptical galaxy at the center of the Able 202 9 galaxy cluster, about 1 billion light years from Earth. The black hole at its center has an estimated mass between 40 and 100 billion solar masses, with most estimates clustering around 50 to 70 billion solar masses. At the high end of estimates, IC1101's black hole would rival TON 618 in size. Its event horizon could extend to 200 billion kilometers or more, encompassing a volume of space that dwarfs our entire planetary system, but perhaps the most extreme black hole discovered in recent years is Phoenix A. Phoenix A sits at the center of the Phoenix cluster, one of the most massive galaxy clusters in the known universe. The cluster is located about 5.8 billion light years from Earth. At its center lies a giant elliptical galaxy, and at the center of that galaxy lies something truly monstrous. In 2022, astronomers published observations suggesting that the black hole in Phoenix A has a mass of approximately 100 billion solar masses. 100 billion solar masses. Let's calculate the Schwarzschild radius. 100 billion times 3 kilometers equals 300 billion kilometers. The diameter of the event horizon would be 600 billion kilometers. 600 billion kilometers. That's 80 times the distance from the Sun to Pluto. That's 40 times the radius of the Kuiper Belt. Light would take more than 23 days to cross from one side to the other. If you placed Phoenix A where our Sun is, its event horizon would extend far beyond any definition of our solar system. The Kuiper Belt would be deep inside the event horizon. The scattered disk objects would be inside. The inner Oort cloud would be inside. Our entire cosmic neighborhood would be swallowed. The scale is almost impossible to process. This single object, this region of no escape, is so vast that our solar system becomes insignificant in comparison. Everything humanity has ever known or explored would fit inside it like a grain of sand in a basketball. And here's something that might be the most counterintuitive fact about ultramassive black holes. Despite their enormous mass, despite containing hundreds of billions of times more matter than our Sun, their average density is astonishingly low. This paradox deserves explanation. We tend to think of black holes as incredibly dense objects, and in one sense, they are. All the mass is concentrated at the singularity, a point of theoretically infinite density at the center. But when astronomers talk about the density of a black hole, they usually mean the average density, the total mass divided by the volume enclosed within the event horizon. As we discussed with stellar black holes, the Schwarzschild radius increases linearly with mass, but volume increases with the cube of the radius. This means that as black holes grow, their event horizons encompass more and more space, while the mass increases more slowly. The average density drops dramatically. For TON 618, with a mass of 66 billion solar masses and an event horizon radius of 198 billion kilometers, the average density works out to roughly 4 millionths of a gram per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Air at sea level has a density of about 1.2 thousandths of a gram per cubic centimeter. TON 618's average density is about 300 times less dense than air. For Phoenix A, with 100 billion solar masses and an event horizon radius of 300 billion kilometers, the average density is even lower. It works out to approximately 2 millionths of a gram per cubic centimeter. That's about 600 times less dense than air at sea level. You could have a region of space with the density of a very good laboratory vacuum, and if that region is large enough, it would still be a black hole. The cumulative gravity from all that diffuse mass would be enough to prevent anything from escaping. This is one of the strangest aspects of ultramassive black holes. They don't feel dense in the traditional sense. If you could somehow survive at the event horizon of Phoenix A, the local environment wouldn't seem particularly extreme. The density would be far lower than the air you're breathing right now. The tidal forces would be imperceptible, but you would still be doomed. The event horizon is the event horizon, regardless of the local density. Once inside, all paths lead inward. The singularity awaits, whether you have seconds to reach it or weeks. This raises an obvious question. How did these monsters form? How did they grow so unimaginably large? The answer isn't entirely clear, and it's one of the active areas of research in modern astrophysics. One possibility is that ultramassive black holes started as ordinary stellar black holes, formed in the deaths of massive stars, and simply grew by consuming matter over billions of years. In the right environment, at the center of a galaxy with plenty of gas and stars to consume, a black hole could gradually increase its mass. But there's a problem with this explanation. There's a limit to how fast a black hole can grow through accretion of matter. When matter falls toward a black hole, it doesn't just drop straight in. It spirals inward, forming an accretion disk. As the matter spirals closer, friction heats it to enormous temperatures. This hot gas radiates energy, emitting light across the electromagnetic spectrum. This radiation creates an outward pressure. Photons streaming away from the accretion disk push against infalling matter, trying to blow it away. At some point, the outward radiation pressure balances the inward gravitational pull. This is called the Eddington limit, named after the astronomer Arthur Eddington. A black hole feeding at the Eddington limit doubles its mass roughly every 40 to 50 million years. This sounds fast, but it's actually quite slow on cosmic timescales. Let's do the math. Starting with a stellar black hole of 10 solar masses and doubling every 50 million years, how long would it take to reach 66 billion solar masses? The number of doublings needed is the logarithm base, 2 of 66 billion divided by 10. That's about 32.6 doublings. Multiply by 50 million years per doubling, and you get about 1.6 billion years. That seems achievable. The universe is 13.8 billion years old. There's been plenty of time for a stellar black hole to grow to ultramassive scales. But here's the problem. This assumes continuous feeding at the Eddington limit for over 1 billion years. In reality, black holes don't feed continuously. They go through active phases when lots of matter is available, followed by quiescent phases when little matter falls in. The average feeding rate over cosmic time is much lower than the Eddington limit. Moreover, we observe ultramassive black holes like TON 618 at high redshifts, meaning we're seeing them as they were when the universe was young. TON 618's light has traveled for 10.4 billion years. When that light was emitted, the universe was only about 3.4 billion years old. That's not enough time for a stellar black hole to grow to 66 billion solar masses, even feeding at the maximum rate. This suggests that ultramassive black holes didn't start as stellar black holes. They must have started bigger. One theory proposes that in the early universe, massive clouds of gas could have collapsed directly into black holes, without ever forming stars. These direct collapse black holes could have started with masses of tens of thousands, or even hundreds of thousands of solar masses. Starting with a larger seed, there's more time to grow to ultramassive scales. Another possibility is that black hole mergers played a significant role. When galaxies collide, their central black holes eventually spiral together and merge, combining their masses. A black hole that has undergone many mergers over cosmic history could accumulate enormous mass. The Milky Way will collide with the Andromeda Galaxy in about 4.5 billion years. Both galaxies have supermassive black holes at their centers. Eventually, billions of years after the initial collision, those black holes will merge. The result will be a single black hole with a combined mass of perhaps 10 million solar masses or more. This process has been happening throughout the universe for billions of years. Galaxies merge, their black holes combine, the resulting black holes grow larger, and the cycle continues. The truth is probably some combination of all these processes. Ultramassive black holes likely started big, from the direct collapse of massive gas clouds in the early universe. They then grew through accretion, consuming gas and stars over billions of years, and they merged with other black holes when their host galaxies collided with neighbors. The result is the cosmic leviathans we see today. Objects so massive they defy intuition. Objects whose event horizons are larger than the solar system we call home. What would it be like to approach one of these ultramassive black holes? In some ways, it would be surprisingly gentle. We've seen how tidal forces decrease as black holes grow larger. For Sagittarius A star, those forces were survivable. For TON 618, they would be imperceptible. You could cross the event horizon without feeling anything unusual at all. This is the great paradox of ultramassive black holes. The most massive objects in the universe have the gentlest event horizons. You would cross the boundary without a scratch, but the gentleness is an illusion. You would still be doomed. Once inside the event horizon, there is no escape. All paths lead inward. The singularity awaits, and for an ultramassive black hole, the journey from event horizon to singularity would be much longer than for smaller black holes. For Sagittarius, a star, the time from crossing the event horizon to reaching the singularity is about 1 minute. For TON 618, the time would be much longer. Days, perhaps. Weeks, even. You would have time to contemplate your fate as you fell through increasingly warped space-time, watching the universe outside seem to accelerate due to time dilation, knowing that no signal you send will ever reach the outside world. Picture what those final days might be like. As you cross the event horizon, you would notice nothing unusual about your immediate surroundings. No flash of light, no physical barrier, no sensation of crossing a boundary. Your watch would tick normally. Your heart would beat normally. Physics, in your local reference frame, would appear unchanged. But if you look back toward the universe you left behind, you would see something extraordinary. The stars and galaxies outside the black hole would appear compressed into a shrinking circle of light above you. As you fell deeper, this circle would grow smaller and smaller, the entire observable universe squeezed into a diminishing window. And that window would be blue shifted, the light compressed to shorter wavelengths as it struggled to follow you into the black hole. The universe would appear to speed up. Hours of external time passing in what felt like minutes to you. Days passing in hours. You would watch the cosmos age before your eyes. Meanwhile, below you, there would be nothing but darkness. No matter which direction you pointed your flashlight, the light would fall inward toward the singularity. You couldn't illuminate your destination. You could only fall toward it. For days, you would fall through this warped space-time, watching the universe shrink above you while darkness expanded below. You would have time to think, to remember, to regret, time to understand that no one would ever know what you experienced. No signal could escape. Your final moments would be yours alone. And then, as you approached the singularity, the tidal forces that had been so gentle at the event horizon would finally begin to grow. In those last moments, even an ultramassive black hole would become violent. The singularity does not discriminate by size. It consumes all equally. What happens when you reach the singularity? We don't know. General relativity predicts infinite density, infinite curvature, but physicists believe these infinities are a sign that the theory breaks down. Quantum effects must become important at such extreme scales, but we don't have a complete theory of quantum gravity to tell us what really happens. The singularity remains one of the deepest mysteries in physics, and ultramassive black holes guard this mystery behind event horizons larger than solar systems. From outside, an ultramassive black hole would be a spectacular sight. The intense gravity bends light in dramatic ways, creating complex patterns of lensed images around the event horizon. Stars behind the black hole would appear as rings and arcs, their light warped by the curved space-time. If the black hole is actively feeding, its accretion disk would be one of the most luminous objects in the universe. TON 618's accretion disk outshines hundreds of trillions of suns. From nearby galaxies, it would appear as a brilliant point of light, visible across millions of light years. These are the quasars that astronomers have studied since the 1960s. The word quasar comes from quasi-stellar because they look like stars when first discovered, single points of light with unusual spectra. We now know they're the accretion disks of supermassive and ultramassive black holes, beacons of light powered by matter falling into the largest gravitational wells in the cosmos. The existence of these monsters raises profound questions about the universe itself. Is there an upper limit to how large a black hole can grow? Theory suggests there might be. Beyond a certain mass, the radiation pressure from the accretion disk might prevent any more matter from falling in. The black hole would essentially choke on its own food. But we don't know where this limit lies. It might be a few 100 billion solar masses. It might be higher. What role do ultramassive black holes play in galaxy formation and evolution? We now know that almost every large galaxy has a supermassive black hole at its center, and there's a close relationship between the mass of the black hole and the properties of its host galaxy. More massive galaxies tend to have more massive central black holes. This correlation suggests that black holes and galaxies grow together, influencing each other's development over billions of years. This relationship, known as the M-sigma relation, is one of the most surprising discoveries in modern astronomy. The mass of a galaxy's central black hole is tightly correlated with the velocity dispersion of stars in the galaxy's bulge, the measure of how fast stars are moving in random directions. The correlation is remarkably tight. If you tell an astronomer how fast the stars in a galaxy's bulge are moving, they can predict the mass of the central black hole to within a factor of 2 or 3. This works for galaxies across the entire range of sizes, from small dwarf galaxies to giant ellipticals. But here's what's strange. The black hole is tiny compared to the galaxy. Sagittarius A star, despite having 4 million solar masses, is only about 100,000th of the Milky Way's total mass. How can something so small influence something so large? How does the galaxy know about its central black hole? The answer seems to be feedback. When black holes actively feed, they release enormous amounts of energy. This energy heats the surrounding gas, preventing it from cooling and forming new stars. The black hole regulates the galaxy's growth, and the galaxy's growth regulates the black hole's feeding. They evolve together, locked in a cosmic dance that spans billions of years. Are there black holes even larger than the ones we've found? The observable universe is vast, and we've only surveyed a fraction of it in detail. There might be ultramassive black holes lurking in distant galaxy clusters that we haven't yet discovered. The largest black hole in the universe might be out there, waiting to be found. We began this journey with Karl Schwarzschild, a soldier scientist, calculating equations in a World War I trench. His solution to Einstein's equations revealed a boundary that seemed impossible, a mathematical curiosity that surely couldn't correspond to anything real. A century later, we know better. Black holes are real. They exist throughout the universe in numbers beyond counting. Stellar black holes with event horizons the size of cities. Supermassive black holes with event horizons millions of kilometers across. Ultramassive black holes with event horizons larger than our entire solar system. The Schwarzschild radius defines the boundary where our universe ends and something else begins. It's a point of no return. An event horizon, a one-way door in space-time. Cross it and you're gone forever, falling toward a singularity where all the physics we know breaks down. From the 3-kilometer Schwarzschild radius of a collapsed sun to the 300 billion kilometer event horizon of Phoenix A, we see the same physics operating across 11 orders of magnitude. The same equations that Schwarzschild solved while artillery shells fell around him describe objects from city-sized to solar system-sized. The true scale of these cosmic abysses is terrifying in the most profound sense. Not scary like a monster in a horror movie, but terrifying in the way that confronts us with the vastness and strangeness of reality. Terrifying because it shows us how small we are. Terrifying because it reveals structures that violate every intuition we've developed, living on a small planet orbiting an ordinary star. And yet, this terror is also beautiful. It's the beauty of understanding, of grasping something about the universe that previous generations couldn't imagine. We are tiny, brief creatures on a small world. Our lives last decades, not billions of years. Our journeys span thousands of kilometers, not trillions. And yet, we can comprehend black holes. We can calculate their sizes, measure their masses, photograph their shadows. The next time you look up at the night sky, remember what lurks at the center of that pale band of light called the Milky Way. 26,000 light years away, a 4 million solar mass black hole sits in darkness, a 24 million kilometer event horizon, marking the boundary of no return. And beyond our galaxy, scattered across billions of light years, there are monsters even larger. Event horizons that could swallow our entire solar system. Masses equivalent to hundreds of billions of suns. Boundaries where time freezes and light is trapped forever. This is the true scale of black holes, from city-sized to solar system-sized, from stellar corpses to cosmic leviathans, from the equations of a dying soldier to the edges of our understanding. The Schwarzschild radius defines where physics breaks, and the universe has built objects at every scale that physics allows. Sleep well tonight, knowing the cosmos contains horrors beyond imagination, knowing that the rules of space-time permit boundaries from which nothing returns, knowing that somewhere, right now, light is being trapped forever, matter is falling past points of no return, and singularities are hiding mysteries we may never solve. The universe is beautiful. The universe is strange. And the universe is terrifying in ways that only make it more worthy of our wonder. Thank you for joining me on this journey into darkness. If you found this exploration meaningful, please consider liking this video and subscribing to the channel. And remember, every time you look at the stars, you're looking at a universe filled with edges of oblivion, event horizons, Schwarzschild radii, the boundaries where our reality ends and something unknown begins. Good night, and may you never find yourself falling toward one.